Select the major product of the following reaction sequence. So looking at our starting material, we have a ketone, and we have a ketone that has conjugated to the carbonyl an alkene. And another way of naming this, the carbon next door to the carbonyl is the alpha carbon. And then the next one would be the beta carbon, and that's an unsaturation. So another way of saying this is that it is an alpha beta unsaturated ketone. And the fact that this alkene is in conjugation with the carbonyl is significant because it means we've got some resonance. So let's just look at this kind of generically. First of all, I'm going to draw a simpler unsaturated ketone. So what I want to recognize when we have an alpha beta unsaturated ketone is that we have two different electrophilic sites because we've got resonance. We can draw a resonance structure to put these pi electrons up in the oxygen, and that's something that we're quite used to with carbonyls. And that explains why our carbonyl carbon is electrophilic. But we also want to recognize we can additionally move this pi bond, which shows us by these resonance forms that the beta carbon is also electrophilic. So we have two electrophilic sites. So when we're dealing with an alpha beta unsaturated aldehyde or ketone, and we're trying to decide where our nucleophile attacks, it depends on the type of nucleophile. So really strong bases that are also strong nucleophiles, things like Grignard reagents, lithium aluminum hydride, things like this will attack at the carbonyl. So these are known as hard nucleophiles, and that carbonyl carbon is your hard electrophilic site where you've got a greater concentration of positive charge. And so things that are weaker bases, or so-called softer nucleophiles, so these might be things like cuprates, like sulfur nucleophiles, cyanide ion. These will attack at the beta carbon. And so that's what we have here, is we have a cyanide ion. And so we can show that adding to the beta carbon. And so this is what it's going to do. So if it attacks that beta carbon, we're going to push these pi electrons here, and then push the pi electrons from the carbonyl bond onto the oxygen. And so we can take a look at what that gives us. And so we see an oxygen with a negative charge, and we see that we have added the cyano group. And this is just under slightly acidic conditions here, and so we do have an acid in solution. I'm just going to write H+. And so what we can do now is we can see these electrons come back down to form the carbonyl, and this position will grab a proton. And so this would be the initial product of step 1. So you're going to have the carbonyl intact, and you will have a nitrile. And so this is the product of step 1. And then we're going to take this molecule that contains a ketone and a nitrile, and we're going to treat this with hydrogen gas and rainy nickel. So I think I'm going to bring it down here to avoid kind of crossing over where we have those resonance forms and the notes we made here. So hydrogen gas and rainy nickel. So these are some pretty strong hydrogenation conditions. Rainy nickel is more reactive than something like palladium on carbon. And so this will reduce your nitrile to the amine, and it will also reduce aldehydes and ketones. So not all carbonyl containing compounds, but aldehydes and ketones will be reduced by rainy nickel. So you'd add hydrogen here and here across that pi bond, so you'd end up with the alcohol. So your ketone will be reduced to the alcohol, and your nitrile will be reduced to the primary amine. All right, so as with all hydrogenations, this is done in hydrogen atmosphere, so you have an excess of hydrogen, right? Because we're adding one equivalent here, 2 here. Don't let that alarm you. We've got lots of hydrogen in this system to do that. And we can see that this matches option C.